Hello again. In this video, we're going to go over section 2.6, part 7, which is about Theorem 214 and Theorem 215. Now, Theorem 214 is about the continuity of inverse functions. And it says, if a continuous function f has an inverse on an interval I, then its inverse function is also continuous. But not on the interval I. It's on the interval consisting of the points f of x, where x is in the interval I. And that's because when you look at the inverse function, the domain and range are switched as compared to the original function f. Okay? All right, Theorem 215 is about the continuity of transcendental functions. And so we have several transcendental functions listed here. The 6 trig functions and their inverse functions, the exponential function, and the logarithmic function. Okay, so for these transcendental functions that are listed here, each of these functions are continuous at all points of their domain. And just to give you some examples, like if you take sine of x oscillates between 1 and minus 1. But it oscillates in a very smooth fashion. You can draw all of sine of x without having to lift up your pencil at any point in its domain. And so it's continuous from minus infinity to infinity. And that's also true for the cosine function. Now, there are some trig functions that are undefined at certain spots. For example, secant of x, and I'll show you the graph of secant of x. The graph of secant of x looks like this, and you can see it's undefined at each of these asymptotes. But nonetheless, secant of x is continuous on its domain. Okay, so for example, between pi over 2 and 3 pi over 2, you can see that this is continuous. You can draw this without lifting up your pencil from pi over 2 to 3 pi over 2. And so this function is continuous on its domain, okay? But that doesn't mean it's not defined at certain spots, right? Okay, so this function's undefined at each of these vertical asymptotes, but it's still continuous on its domain, at every point in its domain. Okay, and so that's what we're saying here. That's true for the 6 trig functions, and it's also true for the 6 inverse trig functions. Now, as far as the exponential functions go, now remember, exponential functions are functions that look like this. They have some base raised to the x power. And one of the more common bases that you'll see is the base e, the natural base. Okay, well, for exponential functions, an example of an exponential function, the graph of like 4 raised to the x power looks like this. And I think you can see that you can draw this without lifting up your pencil at every single point from minus infinity to infinity. And so it's continuous from minus infinity to infinity. Okay, which is every point in its domain. Now, logarithmic functions, let me graph a logarithmic function on the calculator. So here's an example of the natural log of x. The graph of natural log of x looks like this. And this is a vertical asymptote at x equals 0. So it never reaches that vertical asymptote. And I think you can see from this graph that it's defined only for values of x that are greater than 0. So the domain of this function is all x values greater than 0. But on that domain, you can see that it is continuous, right? I can draw this function without lifting up my pencil at every point on its domain. Okay, so this is also true for logarithmic functions. Now, I graphed natural log of x, but this is true for any logarithm with any base for any logarithm, okay? Okay, so the last thing I want to mention in this section is that we can evaluate each of these functions, or the limit as x approaches a for any one of these functions. We can evaluate it by using direct substitution because of the fact that each of these functions are continuous at all points on their domain. Okay, so the limit of f of x as x approaches a will be equal to f evaluated at a because of the fact that they're continuous at every point in their domain. Now remember, this is the very, very definition of continuity, right? This limit is equal to f evaluated at a. Okay, so just remember, you can actually use direct substitution if you're trying to find the limit of any one of these transcendental functions because of the property of continuity on their domains. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.